Hello and welcome back to another lesson on A-level physics. Today's learning intention is to calculate the angle required for an object to topple over. Today's success criteria is to define the terms stable equilibrium and unstable equilibrium and to explain when a tilted object will topple over. Let's begin by looking at the conditions for stable and unstable equilibrium. If a body is in stable equilibrium and it is displaced and then released, it will return back to its equilibrium position. This is because the centre of mass of the object is directly below the point of suspension when the object is at rest. Take, for example, the hanging basket shown in the diagram on the board. If that is first displaced and then released, it is of course going to eventually return back to its equilibrium position, possibly oscillating first, but it will return back to its stable equilibrium position. By contrast, if a body is in unstable equilibrium and it is displaced and then released, it will not return to its equilibrium position. That is because the centre of mass of the object is directly above the point of support when the object is at rest. Take, for example, we have here a beam on top of a cylinder. If that beam gets displaced, it will not end up returning back to its equilibrium position because it'll probably fall off the cylinder, etc. Okay, now let's talk about tilting then. So tilting is when an object at rest on a surface is acted on by a force that raises it up to one side. We have shown here in the diagram on the board an example of this where we've got a force applied to the top of a bookcase. The height of the bookcase is D, or at least the distance between the line of action of the force and the floor is D, and the width or the length of the bookcase is B. Now the forces are shown on the diagram. The force F is applied to the bookcase, which is making it tilt, and the weight W is also acting on the bookcase. The force applied to the bookcase must make it turn clockwise about the pivot, as shown here. The pivot in this situation being the part of the bookcase that remains in contact with the floor. Now the weight of the bookcase will provide a moment in the opposite direction. It will be in the anti-clockwise direction because that would make this bookcase try and fall back down, which will be anti-clockwise about point P. Now the clockwise moment provided by force F would be F multiplied by D because D is the perpendicular distance between the line of action of F and the pivot point. By contrast, the size of the anti-clockwise moment caused by W will be W multiplied by B over 2 because the perpendicular distance between the line of action of W and the pivot point is half of B. Now the condition upon which we are actually going to have tilting occur is if the moment caused by F is greater than the moment caused by W. Now, a tilted object will topple over if it is tilted too far. If an object on a flat surface is tilted more and more, the line of action of the weight passes closer and closer to the pivot. If it is tilted too far, then the line of action of the weight will pass beyond the pivot point and the object will topple over. That will be meaning, in other words, that the weight will no longer be acting through the base of the object. Let's look at an example question. This has come from an exam paper from 2016. A portable basketball set has a base and post arrangement. The post arrangement consists of a post, a backboard, hoop and net. Due to the large area of the backboard, the basketball set may topple over when the wind blows. Calculate the minimum force of the wind, Fw, that will cause the basketball set to be continued to be tilted at the angle shown. Ignore the effect of wind on the base. Now we've been given quite a bit of data in the question. We've been told what the weight of the post arrangement is. It is 27 newtons. We've been told what the weight of the base is as well. It is 868 newtons. And then from there as well, you can see on the diagram that we've got multiple distances shown. We've got the distance 0.45 meters, which is the distance from the centre of mass to the pivot point, and we can see that there's a 2 metre distance between the centre of mass of the post arrangement and the pivot point, and 2.4 metres to where the force of the wind is acting. So let's get to it then. The first thing to consider is going to be what moments are acting, and we'll start off by considering the clockwise moment, which is going to be caused in this case by the weight of the base. Now, the weight of the base is obviously, we just said, is 868 newtons, and we will be multiplying that by the distance to the pivot. But the distance to the pivot is not 0.45 meters. Instead, if we look at this situation here, we can see that the 0.45 meters is not actually at 90 degrees to the line of action of the weight, and so instead we need to work out the side of the triangle that is going to be perpendicular to the weight of the base. So I've drawn as part of my working out that triangle again, where we can see that it's 0.45 meters, the centre of mass is away from the pivot point, but we want to work out the perpendicular distance to the weight of the base. Now, because the vertical post is 15 degrees tilted, that means that the base will be lifted up by 15 degrees as well. So I can include that on my triangle and then work out what that length is going to be. Now, because I'm after the adjacent side, I will do 0.45 times by cos 15, which gives us a distance of 0.43 meters. So to work out the moment that is caused by the weight of the base, we take the weight of the base, which is 868, and we will multiply that by 0.43 to give us an answer of 373.24 Newton meters. Now we need to consider the anti-clockwise moments. There are going to be two forces here that cause anti-clockwise moments. We have the weight of the post arrangement and the force of the wind. We'll deal with the weight of the post arrangement first because we know that that has a weight of 27 newtons. Now, unfortunately, the distance of 2 meters is not perpendicular to the weight of the post arrangement. If I just highlight this triangle here for you on the board, you can see that what we'd actually need to work out is the bottom side of that triangle, because that would be perpendicular to the direction that the weight is acting. So I've redrawn that here as part of the working out. I know that the hypotenuse of the triangle is 2 meters, and by the z-angle law from maths, if you remember that from GCSE, because the angle between the vertical and the post is 15 degrees, I can see that the angle inside that triangle is also 15. This time I'm working out the opposite side, so we'll do 2 multiplied by sine 15 to give us a perpendicular distance of 0.52 meters from the line of action of the weight to the pivot point. We now multiply that, of course, by the weight of the post arrangement, which is 27 newtons, and that comes out as 13.98 Newton meters. Now, the last thing to consider is, of course, the force of the wind that we're actually trying to work out. We know that the force of the wind is also providing an anti-clockwise moment, and we know that it is going to be 2.4 meters away from the pivot point, but again, that is not the perpendicular distance. I've highlighted for you here on the board the triangle that we will consider, and that vertical line is the one that will be perpendicular to the line of action of the force of the wind. So we want to work out the length of that vertical side, knowing of course that the hypotenuse is 2.4 meters, so we would do 2.4 multiplied by cos 15 because we're working out the adjacent side, and that gives us 2.32 meters. Now then, we don't know the value of Fw, but we can say that the moment it is causing is 2.318 Fw. Now, by applying the principle of moments, for this to be continued to be tilted, it must be in equilibrium, so the clockwise moments have to equal the anti-clockwise moments, so 2.32 Fw plus 13.98 has to equal 373.24. We subtract 13.98 from both sides, divide by 2.32, and that should give us an answer of around 155 newtons. If you had a go at this yourself before watching the working out through, you might have a slightly different answer depending on how you have rounded at different stages in the calculation. But as long as you're coming out of between 155 and 158, then you will have got the question correct. Okay, now I'm going to present to you 3 sets of questions. I want you to have a go at a minimum of 2 of these sets of questions. Pause the video while you're doing them and then use the video to check your answers and obviously highlight any areas that you need to improve on. So the first question on consolidation says, define the following terms: stable equilibrium, unstable equilibrium, and the principle of moments. So A and B come from earlier in today's lesson. Stable equilibrium is when an object is displaced from equilibrium but will return to its original equilibrium position after being released. Unstable equilibrium is the polar opposite. It is when an object is displaced from equilibrium but it won't return to equilibrium position after it has been released. Now, the principle of moments we established a couple of lessons ago, that states that in equilibrium, the sum of the clockwise moments must equal the sum of the anti-clockwise moments. Question 2. Explain why a bookcase with books on its top shelf is less stable than if the books were on the bottom shelf. Well, simply put, that is because the centre of mass is going to be higher up if the upper shelves are filled instead of the lower shelves. If it is tilted, it will topple over at a smaller angle when the upper shelves are full than if they were empty. Okay, let's now look at some standard demand questions. An empty wardrobe of weight 400 newtons has a square base, 0.8 metres by 0.8 metres, and its height is 1.8 metres. A horizontal force is applied to the top edge of the wardrobe in order to make it tilt. Calculate the force needed to lift the wardrobe base off the floor along one side. So I would actually redraw out that wardrobe to begin with, because we can show that there's a 400 Newton force acting downwards, and we can obviously label F and 1.8 metres on here as well. Now, the force F that is making it tilt will provide a moment that is equal to F times 1.8. The weight is going to be providing an anti-clockwise moment, which is equal to 400 times 0.4, because obviously the centre of mass is in the middle of the wardrobe, and that perpendicular distance will be 0.4 metres. We can then, of course, set those equal to each other, and dividing by 1.8 means that the force needed to lift this up will be 89 newtons or greater. Question 2. A windsurfer of mass 60 kilograms is surfing in a crosswind of 165 newtons. The wind applies a force to the sail 2.5 metres above the surfboard. In order to prevent the wind blowing the windsurfer over, the windsurfer leans into the wind as shown in the diagram. How far must the windsurfer lean out from the board D so that his weight W will be sufficient to stop the board from tilting up out of the sea? Now, to start off with, we need to appreciate that we've not actually been given the weight of the windsurfer, we've been given their mass. So we must do W equals M times G. So we do 60 multiplied by 9.81, which gives us 588.6 newtons. Now that we know the forces involved, we can now begin to consider applying the principle of moments to this situation. The wind, which provides the 165 Newton force, is 2.5 metres away perpendicularly from the pivot point. So the moment that causes is going to be 165 times 2.5. The clockwise moment is provided by the weight at a distance D away perpendicularly from the pivot point. So when we equate those equal to each other, D would be 165 times 2.5 divided by 588.6, which gives us an answer of 0.7 metres. Okay, the stretch and challenge question has just got one question of two parts. It says a vehicle has a wheelbase of 1.8 metres and a centre of mass when unloaded, which is 0.8 metres above the ground. The vehicle is tested for stability on an adjustable slope, and we've been asked to calculate the maximum angle of the slope to the horizontal if the vehicle is not to topple over. Now, in the exam, I would definitely be drawing a diagram. I might draw on the actual diagram given to me, depending on how much I need to use this diagram for later on, but here I'm going to redraw it on the board. So you can see that I've drawn the centre of mass being 0.8 metres perpendicularly above the slope, and then of course I've drawn this whole this car as a box whereby the slope is at an angle theta. Now the car will topple over once the weight or the line of action of the weight passes beyond the wheelbase. Now I'm just going to take out the laser pointer on PowerPoint so that I can show you what I mean. So from the centre of mass, where I put the laser pointer here, the weight would act vertically downwards. Now as the angle theta gets bigger and bigger and bigger, this line of action will get closer and closer to the pivot point until eventually theta is so big and the angle is so large that this vertical line actually lies outside of the wheelbase. That is when toppling will occur. So what we can work out is the angle between the wheel and the centre of mass, because we know that the two wheels are 1.8 metres apart, so therefore this distance here on this triangle will be 0.9 metres. We know that it's 0.8 metres above the actual surface, so we can work out the angle here, which I've labelled phi, by doing tan theta is opposite over adjacent. So that means that the angle is going to be tan to the -1 of 0.8 over 0.9, which comes out as 41.6 degrees. But we weren't asked in the question to work out the angle when you draw a line from the wheel to the centre of mass. We were asked to work out the angle that the angle of the slope, the adjustable slope, will be at when it topples over. So when it topples over, then we can say, well, we know that this vertical line is making a 90-degree angle here with the horizontal. So if we know that the angle here is 41.6, then this angle plus the angle theta has to be equal to 90. So therefore theta is going to be 90 minus 41.6, which gives us an answer of 48.4 degrees. Then finally, part B says, if the vehicle carries a full load of people, will it be more likely or less likely to topple over on a slope? Explain your answer. Now, as you can see from the diagram, people are going to be sitting, if you look here, people's bodies will be sat above the centre of mass of the car, and so because the centre of mass has been raised, we can say that it will topple over on a less steep slope, so it will be therefore more likely to topple over.